Okay, so we talked a little about percent ionizations of weak acids, where once you fall below 5% ionization, usually the minus X is negligible because the reaction relies so heavily to the left that it's not necessary to actually subtract the initial concentration from the amount of H ions in solution because it's so small. But here, we found that the percent ionization of niacin in a 0.02 solution was 2.7%. Very little ionized. But look at the concentration, that was really large. Here they want you to try to calculate the percentage of niacin molecules ionized when it's 0.010. So we learned on that graph that the more concentrated the acid gets, actually the less that gets percent ionized, right? The less gets ionized at a higher concentration. But now, at 0.010, it may not be negligible because now the initial concentration is so low. Okay, so here we're going to have to make an ice table to calculate the percentage of niacin molecules ionized in this kind of solution, and they're giving us the Ka. So here's the formula for niacin in aqueous solution. We know that when this thing dissociates, when it dissociates very little, you keep everything else here. Remember, you lose the proton, that becomes negative, and then you got the H ion. So we know that this ion here is not really that important, but we're really worried about this. So here we make a little ice table. Right, initial change and equilibrium concentrations. Okay, so try to fill out this table the best you can before watching the rest of this. Okay, so you know that if you're starting with initially a concentration of 0.010, it should be here. You know any change is going to be minus on the left side because it's disappearing, but on the right side it is appearing. We started off with 0 here, right? So we don't know any equilibrium changes, but we know it's going to be minus X, this is going to be plus X, this is going to be plus X, so this becomes XX, and this becomes 0.010 minus X. So pretty much in this case, we've been saying that this is negligible over here because it's such a small value, but because the concentration is so low now, the percentage ionized might be actually higher than 2.7%. So that we need to that's what we're going to find out. So here is the equilibrium setup, right, with Ka with the products over reactants. This is what it would look like, but now we're going to plug in the values here, here, and here. So what you're going to have to do here is set this up into x squared plus bx into the a, b, c, and use the quadratic formula and find out your two values of x. Okay, so if done correctly, these are your two values for x. Obviously, this one can't make sense because you can't have a negative change for x if it's appearing here. So your x value is this. So you plug this into here, and so the H concentration here would be 3.78 times 10 to the negative fourth. Remember, percent ionized is going to be how much actually dissociated at equilibrium concentration. So it's 3.78 times 10 to the negative fourth molar over the initial, in this case, which was 0.01 big M times 100, and the percentage is 3.8%. I mean, and it does make sense because it did get less concentrated, right? Less concentrated means higher percentage was ionized, but we were still below 5%. So we could have actually hypothetically made this negligible, but it's very hard to tell. But usually, rule of thumb is when it's negative 5 or less than that, it's usually negligible, which means if Ka goes less than negative 5, generally is negligible to the fact that this dissociates so little that you can omit this and you can avoid all of this crap so that you're not doing the quadratic formula and you can save yourself a lot of time because we know weak acids don't ionize well.